Oh yeah, that glitched. No, my professor was like the lab assistant would do like almost everything for us. So like as long as we did it with him, and like he would ask us if we understood everything and like what we would do next.
Mm-hmm.
It was a lot less structured than this.
Uh-huh. Yeah. Okay, so again, good morning, everybody. So, couple of reminders. You have such a busy week as far as submissions are concerned. Check your CASA calendars. I guess you have a quiz due today, and then you have some tests due, I guess, on Friday or Saturday, and another quiz on the weekend. So just double check your CASA calendars. There's a lot of things that you need to submit, and it's just the second week of classes, but I guess we can't do anything about that. And also, some of your classmates told me you had some problems with the lecture today, some glitches with Microsoft Teams. So, so that's a bit of a blessing in disguise because that gives us more time to answer the rest of worksheet number 2, which focuses on the mean value theorem and average values for integrals. And then probably towards the end, I can start a quick recap of how to set up integrals that will give you the areas of regions, which is basically what you should have covered earlier in the lecture and what I guess you were sent a material to or a video to watch on that. So yeah, I'll give you a quick review and then give you a couple of quick examples. Um, by the way, I left a poll in the lab meeting channel. It's just I just want to get your feedback about how the lab is being handled so far. Kindly, if you have time, answer the poll. There's just 3 questions. How do you think about the pace of the lab? Uh, the level of difficulty of the problems we're answering here, and any comment or suggestions that you might have for the improvement of the lab. I just want to hear it from you guys so that I know whether I need to adjust the pace or the difficulties of the questions, or yeah, anything that I can do in particular to make this lab more helpful to you. So it's an anonymous poll, so you can give your honest comments there. Yeah. All right, so now let me go to worksheet number 2. I guess you see my screen. Okay, let me just browse through it. Is it also stuck with you guys? Because I'm looking at my other monitor and it looks stuck. Hello, guys. You still there?
I can see it.
Uh, I can see it, but it's stuck.
Yeah, it's
Yeah.
like kind of frozen.
Let me just restart. Hopefully, we won't get the same problem as you had in the lecture. Okay. Let me try it again. Okay. Come on.
There's nothing there yet.
Yeah, I should be. Well, it just worked fine an hour ago when I did my other lab. Another try. Okay. Come on. Yeah, I needed to retry it once more because the previous attempt didn't work. Okay, so you're seeing my screen now, but if I flip to my annotator, yeah. Let me try again once more. Okay. Okay, finally. So I hope everything is fine now. Plus, you got a glimpse of my very convoluted home screen. But anyway, so do you see a problem? Yeah. Okay. Probably let's start with problem number 3. Let me know if you're seeing it well.
I can see it.
Okay, good. So let's start. Problem number 3. Just a quick recap. Part A of this set of problems tells us to find the average value and then compute for the value of C guaranteed by the mean value theorem. Okay. So the only thing, the difference with the difference of problem 3 from problems 1 and 2 is that the function given is quite parametric in form, meaning it doesn't explicitly give the constant values. We needed to explicitly see what the function looks like. It's kind of abstract because you are given arbitrary values m, b, and also the interval is given from 0 to a. But nevertheless, you can solve the problem by simply treating m, b, and a as any other constant, just remembering that x is the lone variable here. So to find the average value, okay, so all we need to do is to apply the formula. So it's 1 over the length of the interval. The interval is from 0 to a. The length can be computed as the right value minus the left value times the integral from 0 to a of the function f. But the function f is mx plus b dx, right? And maybe it's quite baffling to see a lot of variables in the integrand, but if you look at the differential, it has a dx in it. So that means in the integrand, any other variable other than x that you see present should be treated as constants. So that means m and b are just constants. We just don't know their exact values, but they are real numbers. So in the integration step, I'll just treat them as constant multipliers. So bearing that in mind, I can simplify this as 1 over a. The integral of mx plus b is mx squared all over 2 plus bx, right? Evaluated from 0 to a. Again, the lone variable is x, so you integrate with respect to x. M and b are just constant multipliers, all right? And then we carry out the integration. So I'm going to have 1 over a times, I plug in x equals a, and then I'm going to plug x equals 0. But if I plug in a, I'll have m a squared over 2 plus ab. So I replace all x's by a minus, I am supposed to plug in 0 into the antiderivative, but plugging x equals 0 in will get just a bunch of zeros. Okay, and then here I'm gonna have 1 over a times ma squared over 2 plus ab. Brian, what are you referring to? Are you referring to a plus c that comes in the integration? Well, for definite integrals, you can't forget about the arbitrary constant plus c, because anyway, that plus c will be canceled. But if you're doing an indefinite integral, meaning if your integral doesn't have bounds, then you need a plus c. But if you have bounds, just as like in this one, we have the bound from 0 to a, then you don't need the arbitrary constant plus c, right? You can put it there, but it will just cancel away. So for definite integrals, that's not important. But for indefinite integrals, the plus c really matters. Okay. And then I can carry on the simplification here by multiplying both terms by 1 over a. I'm going to get ma over 2 plus b. So the average value is ma over 2 plus b, right? And that's a constant value because we know that ma and b stands for some constant that we don't know the exact value of. Okay? Is that fine? Okay, now the follow-up question is, what is the value of C that is guaranteed by the theorem? So remember now, what we want to do now is to compute, to solve for the equation f of C equals the average value, right? But without knowing the calculations or knowing the things that we did earlier, can you guess what is where will that value C be? Or where will the average value occur? Now the thing here is, what is mx plus b? Mx plus b is a linear function, so it is a straight line, right? It's just a straight line. So where do you expect to get the average value of the straight line if you are on the interval 0 to a? Any guess? So if you have a straight line, where do you expect to get the average value? Which
At
would be
any
a
point.
good guess for C. Yes, Robert?
At any point.
At any point, try again.
The origin.
Try again, Kevin. You have a straight line like this. Where do you expect to get the middle value or the average value?
In the slope?
In the slope? Nope, try again.
Can
In
it
the
be the
exact middle of
y-intercept?
the interval.
Come again. Rohel, what's your guess?
The y-intercept?
The y-intercept? Nope, try again. Robert?
In the exact middle of the interval.
Exactly. It should be at the exact middle of the interval. Remember, the average value is the middle value. The middle value between here and the lowest function value, right? And it's a straight line, so sort of the educated guess here, or the nice hypothesis here, is that the average value will occur at the middle. And let's see if that will be true. So let's all for C, because C would be the value where we attain the average value. So plugging C into the function, we get MC plus B. And we know the value of the average value is MA over 2 plus B. And then I can subtract B from both sides. I'll get MC equals MA over 2. And then I can divide both sides by M. So I get C equals A over 2. And true enough, A over 2 is the middle of the interval 0 to A, right? So yeah. So without even the knowledge of the average value, you can pretty much guess where the average value will occur. But that is because the function given was very simple. It's just a straight line. So the middle value will occur at the middle of the interval. But for complicated functions, some wiggly function, higher order polynomials, those exponentials and so on, finding the average value might be a little bit tricky. Or the C value where the average value will occur will require a lot of work. All right. So let's see, what else did we leave behind from this worksheet? Okay, let's try problem 5. Given that the average value of an even function f on 0, 3 is 2, find the integral from -3 to 3 of f of x dx. Now it's a word problem. So usually the first thing about word problems is look at what is being asked. So here we need to find this value. So that's our end goal. Find that value, find the value of that integral. Now the second step is, what are the given facts? What are the things that we can use to lead us to the final answer? Well, what are the given info here? We know that f is an even function, right? So maybe we need to recall what an even function is. A function is even if the function evaluated at -x is the same as the function evaluated at x. So that's the definition of an even function, when f of -x is equal to f of x. And examples of even functions would be x squared, x to the 4th, x to the 6th, x to the 8th, or in general x to the n, where n is even. Another example of an even function is the cosine function, all right? Also the absolute value function, meaning the function value to the left of the origin is equal to the function value to the right of the origin. And Kevin's suggestion is correct. Instead of computing the entire integral, so you can just compute half of the integral and multiply it by 2. And I'm going to show in details why that is true, right? So, okay, so that's one information. The other information from the problem is that the average value of f is 2 over the interval 0 to 3. So mathematically, that means that f ave is equal to 2. But the formula for that is 1 over the length of the interval. integral from over the interval of f of x dx. So here we know that 2 equals 1/3 the integral from 0 to 3 of f of x dx. Or I can multiply both sides by 3. So I will know that f of x dx has an integral equal to 6 over the interval 0 to 3. Good? And that's the information we recovered from the problem. And we're going to use this info in order to answer what is being asked. So we were told to find the integral from -3 to 3 of f of x dx, right? But the only info we have about this integral is that when you integrate from 0 to 3, the answer is 6. So that means I will split the integral up into 2 pieces. Oops. Instead of integrating it as a whole, I will integrate it first from -3 to 0, and then from 0 to 3 of f of x dx. All right. But the thing here is we already know this value, right? That's equal to 6. And we need to evaluate the remaining one. But if you look at that, I'll use the property of f being even, right? So in order to see it exactly why, as Kevin suggested, we can simply multiply 6 by 2 to get the average value or to get the value of the integral. The reason why we can do that is this. I can let u equals negative x in the first integral. Then there, du will be equal to negative dx. So the first integral, -3 to 0 of f of x dx, will simply be, after the substitution in u, will be f of negative u, negative du, right? And then the bound should also be changed. X equals -3, but if x is -3, then u will be +3. If x is 0, then u would be -0, but -0 is also 0. So I'll have this. And then I'll put the negative sign in front of du out of the integral. Okay. But, okay, 0 to 3. I will interchange the order of the integral because I know an info about the integral from 0 to 3. And here I am evaluating the integral from 3 to 0. So might as well reverse the order. Instead of 3 to 0, I'll do 0 to 3. But that comes at a cost, right? The cost is the negative sign in front. So whenever reversing the order of integration, you put the negative sign in front of the integral, but there's already a negative sign before, so they become a positive sign. All right. And then I'll do a superficial change of variable here. So here, oops, what happened? So here, I can, so integral from 0 to 3, I can replace all u's I see by x. A simple superficial change of variables, right? But the bounds will change. Just imagine letting u equals x. So that's just a change in variable. But I'll use the other info that we haven't used yet. We know that f is an even function. And f being even means this happens. F of -x is the same as f of x. So here, I'll have integral from 0 to 3, f of -x. F being even means that is also the same as f of x dx. And we know the integral from 0 to 3 is just equal to 6 as before. So therefore, we have this integral. Oops. Is equal to the first integral here. We know that's equal to 6. The second integral already, we know that's also 6. So you get value equal to 12. And this is why Kevin's suggestion is correct all along. So if you have an even function, instead of integrating from -a to a, you can simply integrate from 0 to a and then multiply what you get by 2. All right. And I guess we have seen this example or a similar one from before when we tried to look for the absolute average value of the absolute value of x. The absolute value of x is an even function. And so even if we split the integral into two pieces, we just ended up multiplying one of the integrals by 2 because of the symmetry with respect to x equals 0. All right, all good? So this is a long solution, but I guess from now on you can simply say f is even. And so I'll just multiply the integral from 0 to 3 by 2, and that's fine. I just want to show why that is true, right? Any questions? You're pretty quiet in the chat. I hope everything's going well. Okay, I'll take your silence as a yes. I'll assume it is a silence of type 1. I don't know if I mentioned last time. I believe there are 2 types of silence in a class. First silence, or first type of silence, is that you understand everything to the point that you don't have any question. You don't need any clarification. The second type, though, is complete opposite. You don't understand anything at all, not enough to craft a sensible question. So I hope it's a silence of type 1. If it's a silence of type 2, do not be shy. Just let me know, and I'll be happy to walk you through again the solution. Okay. The point is, I want you to take advantage of the lab to really understand the concepts and understand the process, so that when you come to your quizzes or to your exams, you know what to do. Okay, if that's the case, let's go to problem 6. Oh, go ahead, Rohail.
Sorry, I was just looking over it again. So can you explain why you replaced it with u? Because I know you're trying to prove that from -3 to 0 f of x dx is the same thing as 0 to 3 f of x dx. But I don't get why it was replaced by -u and -du.
Okay, yeah, the idea there is I want to use the fact that the function is even, and this is the definition of a function being even, right? So I should have a negative sign inside the function. So I only have the function f with an x inside of it. So the only way I will have a negative sign inside the function f is if I use this substitution. If I let u to be equal to -x. So I have x. I will replace it by u, but from this statement, u equals -x, that means x is equal to -u. So x was replaced by -u, and then du equals -dx means dx is equal to -du. That's why I got dx here replaced by -du. Right? Does that make sense?
Yes, sir. Thank you.
Yeah. And again, the reason is because I want to conform to what an even function is. It has a negative sign inside the function f. Go ahead, Robert.
Instead of like writing and substituting for u, couldn't we just write a sentence out that's saying it's an even function, and therefore like it can be at -x can be evaluated the same as x, so therefore it's a reflection?
Yeah,
because that's in my head, that's what I was thinking the entire time, was it's just a reflection, so it can just be evaluated 2 times 1 interval.
Right. From now on, you can do that. And the reason why you can do that is here. I have just proven that it is correct. And since it is proven in class, then you can use it in your exams or quizzes. Just add a single line or a single sentence saying that you're right. The function is even, so I can do this. Instead of evaluating or doing this substitution or evaluating the entire integral, I can just integrate half of it and multiply the answer by 2, right? So the only point of this long solution is to convince you that that is really true. And I hope you were convinced. And from now on, you can use that argument in future quizzes or exams. Okay. All right, so let's try problem 6 then. So for problem 6, we need to find the average area of all circles with radii from 3 inches to 6 inches. So keyword here, we need to find the average of all the areas of circles with this radii. So in other words, we only need to find the average value, f ave, with what function, f? What will be the function f here? And what is the interval?
Wouldn't it be the function for area of a circle?
Exactly. So that's going to be pi r squared, right? So I'll use a function here of r over what interval? So the interval should be defined in terms of r, and the given radii range from 3 until 6, right? So I guess at this point, it's pretty straightforward. The average value, according to the formula, is 1 over the length of the interval, right? So that's right minus left bound. Integral over the entire interval of the function f pi r squared dr with respect to the variable r. Then we simply carry out the calculations here. So it's going to be pi r cubed all over 3. That's the antiderivative of pi r squared with respect to r, evaluated from 3 to 6. And then this would be a 1/9 pi r cubed, evaluated from 3 to 6. And then this is 1/9 pi of 6 cubed minus 3 cubed. And I guess this simplifies to 21 pi. Yeah, I pre-calculated the results using a calculator so I don't mess it up like what I did last time. By the way, I mistook 16 times 5 to be 80 instead of the right 190. Probably I'm thinking about 16 times 5 instead of 5 times 16. So yeah, or the other way around. Yeah. So I posted a correction there, but I guess this is straightforward. Any clarification with this one? Okay. I hope that's a silence of type 1. Let's go to problem 7. Problem 7, let f be a continuous function. Prove that if f is an odd function, then its average value over any interval of the form negative a to a is 0. Now, this is in contrast to what we have discovered about even functions. For even functions, the value from negative a to a is twice the value from 0 to a, right, of the integral. But if your function is odd, it says that the average value is equal to 0. And let's see why. First thing to recall is the definition for an odd function. F is odd if and only if. I use IFF for the phrase if and only if. F of negative x is negative f of x, right? Example of odd functions: x, x cubed, x to the 5th, x to the 7th, x to the 9th, and so on. In short, those powers x to the n where n is odd. Another example would be the sine function. It's also odd, right? And then let's see. Let's look for the average value. And we were told to prove that the average value is equal to 0, right? So the formula again is 1 over the length of the interval. The interval is from negative a to a, so it's going to be a minus negative a times the integral over the interval of f of x dx, right? So this is going to be 1 over 2a. And then the information we got is that the function is odd. And for being odd, we know this is the property. So that signals that I'll split the integral from negative a to 0 plus the integral from 0 to a of f of x dx. And I hope that these two guys will cancel each other out so that the answer would be 0 times 1 over 2a. And there you go. F of a is equal to 0. So let's see why. To see that, I'll compute the first integral, negative a to 0 of f of x dx, right? So I'll use the same trick I did before. I'll use that same substitution because the definition for an odd function requires a negative sign inside the function f. So the only way I can do that is to let u to be equal to negative x. That's equivalent to saying that x is negative u, right? And then du would be negative dx, which is exactly the same as saying that dx is negative du. And so the integral would be what? F of negative u times negative du. And then here I have x equals negative a. I need to translate that bound into a bound for u. So if x is negative a, u will be positive a. If x is 0, then u will still be 0. So I have that. And then again, I'm going to put the negative sign in front. That negative sign came from the du, because remember we had a negative du. But again, I will interchange also the bounds for the integral. Instead of doing a to 0, I'll do 0 to a. And that will kind of nullify the negative sign in front, because reversing the order of integration comes at the cost of a negative sign in front, right? And then here I'm going to do a superficial change of variables. So I'll just replace all x's by u. So I'll have negative x du, okay? Sorry, dx. Again, you can imagine as it as letting u to be equal to x, and du is equal to dx. The bounds won't change, only the variables will change, because if x is 0, then u is still 0. If u is a, then x is equal to a. That's fine. And then I'll use the fact that f is odd. Since f is odd, so this would be f of x dx, since f is odd, right? Then finally, I'll put out the negative sign in front, and there we go. Here we discovered that the integral from negative a to 0 is equal to the negative of the integral from 0 to a of f of x dx. So therefore, the average value, which we know to be 1 over 2a, times the sum of the two integrals. The first integral is this, but as per our calculations, that integral is just the negative of the integral from 0 to a of f of x dx, plus I'll just copy the second term. And true enough, as we have hoped for, the two integrals cancel each other out. And so the average value is indeed 0, and that's the end of the proof. All right. And that's it. Any follow-up with that? Any clarificatory questions? Did I go too fast on that? Or is it fine?
Yeah. Oh, you did go a little fast, but I understood it.
Mm-hmm. The good thing about this is from now on, if you recognize that the integrand is odd, it's an odd function, then whenever you are asked to evaluate the integral from negative a to positive a, then you can just say, oh, it's an odd function. I'm integrating with respect to a symmetric interval, negative a to a, then the integral will be 0. You don't need to go through this entire process. So just in summary, if your function is even, you get twice the integral from 0 to a. If the function is odd, then the integral will just be 0 from negative a to a. And the reason why that happened is exactly this one. All right. And I think that completes worksheet number 2. So shortly after our meeting, I'll upload this worksheet, or I'll update the one in my website to reflect all the additional solutions we had today. Okay. Right. So can we leave worksheet number 2 now and go to worksheet number 3? No reactions. I'll take that as a yes. Oops. That's for the other class. World of 4. There we go. Okay. So this worksheet contains problems for section 7.3, which is computing areas using integrals, and section 7.4, computing volumes using integrals. I guess you started with section 7.3 already, and I learned that you have answered some basic questions about the examples in that section. So maybe I can go ahead and work with some of these examples. For those who have seen my the initial version of section 7.3, I mean, if you downloaded the file minutes after I uploaded it, you might have an outdated file because I changed 2 problems when I'm trying to review the worksheet. I found that some of them are very difficult or doesn't make sense, so I need to change a couple of problems. Specifically problem 7. I turned it, look at the highlighted portion. That's the edit I did, and problem 15 as well. So, okay, just for those who downloaded it early. Okay, let's try problem 1. Oh, but before I do that, let me give you a quick recap of the concepts here. So the idea here is we will use integrals to compute the area of irregularly shaped regions. I mean, actually, this works for any kind of region. Maybe this is one way how to derive the formula for the area of a triangle, for the area of a square, for the area of, say, an oval, and so on. All those formulas that we have learned from geometry can be derived using this technique that we will be studying. Also, have you ever wondered how land surveyors were able to compute areas of irregularly shaped lots? I mean, lots that are not in the shape of a square, a rectangle, a regular trapezoid, or any pentagon. So those irregularly shaped regions that might be bounded by a river, by rugged terrain, and so on. Since even if we don't have any formula for those irregularly shaped regions, they were able to compute the area of the lots to be inputted in the titles for those lots, right? So the idea is you can do integration, and the only requirement for using integrals is you know what are the bounds, or what are the graphs, or what are the functions that bounds the region. So for instance, let's see this. If I have this function, or if I have this region, let's say is bounded above by y equals f of x, and bounded below by, say, another function, y equals g of x. And I want to compute the area starting from x equals a until x equals b. So that means here, there, and I want to get the area of this shaded region. Okay. And that's my problem. Find the area of this shaded region. Well, it turns out it's easy to compute it using integrals as long as you know what are the functions f and g, and if you have an idea of how the graph looks like over the interval AP. Well, the first thing is to decide what type of strips to use. For this particular example, it would be, oh, the better choice would be to use vertical strips. And I will tell you later why vertical strips are more convenient here, because whenever working with vertical strips, for vertical strips, I'm going to use VS all throughout the class to represent it. So for vertical strips, you use dx. You use x as your variable of integration. So if I'm going to set up the area for this region, I know it would be some form of an integral. If I have decided to use vertical strips, I'll put dx right away. Okay, and that dx will signal to me that the bounds for the integral should be bounds for x. What are the x values that are covered by the region? Well, the region started at x equals a, and it ended at x equals b. So that means the bounds, being bounds for x, are properly a and b respectively. All right? So vertical strips, you go with dx and then bound the x. X starts from a and ends at b. So those are your bounds. And then the integrand would be the height or the length of the vertical strip you used. So in this case, this is the vertical strip we used. We need to compute how long is that strip, right? And the formula for vertical strips is always top minus bottom. The upper function minus the lower function. So in that case, the length or the integrand would be f of x minus g of x. And then once you set it up right like that, you just need to use the techniques of integration that you learned before to get the exact area. So that's how you use vertical strips. Now there are some instances wherein it would be easier to use horizontal strips. For instance, if your function looked like this, so if your function is given in terms of y, and say another function here, and say that is x equals f of y, right? In these cases, it might be somewhat beneficial to use horizontal strips instead. Now, if you have a horizontal strip, right, or HS for short, you use dy. And this is true even for section 7.4. So you can burn into your minds, vertical strip goes with dx, horizontal strip goes with dy, okay? So now the area will be given by an integral with respect to y, okay? Now dy, I have a dy, so the bounds should be with respect to y. So you should look for what is the y value where the region starts and the y value where it ends. So that means here, if that's the region, it started at this y value, let's call that c, and it ended at this y value, let's say that's d. So the integral will be bounded from c until d. Okay? And then what would be the integrand? The integrand would be the width of the horizontal strip that we drew earlier. How to compute the width? Well, the width would be right minus left. So in this particular case, the integrand would be right function minus the left function. And remember, the variable for horizontal strips is y. So you should not have an x whenever using vertical strips. So all are given or should be computed in terms of the variable y. Okay? Okay, question, Robert?
I'd just like to simplify this in my mind. Like, so f of g, we're taking the area of the upper function and the area of the bottom function and then subtracting them to find what's missing, like in between.
Yeah, something like that, yeah. Okay, so again, dx goes with vertical strips, dy goes with horizontal strips. Might be mindful of the bound. So dx, everything should be given in terms of x, dy should be given in terms of y. Now we see here that since we are calculating the length of the strips using directions, I mean top minus bottom, right minus left, it is important that you have a good idea of how the graph looks like, right? So what function goes on top, what functions goes in the bottom, or what is the right function, what is the left function. So I suggest at least you review how to sketch the graph of basic functions, maybe coming from your pre-cal classes, your algebra classes, or perhaps curve sketching from Cal 1. Right? I guess we'll see an example where I will use concepts from Cal 1. But let's start with an easier one, which is problem number 1 in this worksheet. So we need to find the area of a triangle with vertices at 0, 0, 1, 5, and 1, 6. Okay. Now let's have a quick picture of how the triangle looks like. Of course, you can use some formulas you learned from geometry or some techniques you learned there, but you're expected to use calculus concepts since this is a calculus class. So let's do it using calculus. The first vertex is at the origin. The next vertex is at 1, 5. Okay, my figure is not drawn to scale, so I'll just label them properly. And then the third vertex is at 1, 6. It's there. And it's a pretty awkward looking triangle. So this is the triangle that we want to find the area of. Okay. Now the thing here is, it looks like using vertical strips would be easy here, because the red function is always on top and the blue function is always at the bottom. So a vertical strip setup here is pretty much convenient, right? Now, but unfortunately, we don't know what are the functions representing those two lines. So I need to compute. I need to determine what are the equations of the red and the blue lines. So I hope you remember how to compute for or how to find the equation of a line passing through 2 points. So for instance, for the red line, let's call f to be the function passing through, or the line passing through the origin, and 1, 5, and 1, 6 rather. That's the red line. And then if you remember, the formula for the equation is y minus y1 equals the slope times x minus x1, right? And then I will pick this one. This would be my y1, and this would be my x1. Of course, you could have chosen 1 and 6 to be your x1 and y1 respectively, but it's always easier to work with zeros. So I'll choose that. So I'll have y minus 0 equals the slope. The slope m between 2 points is just the change in y. So subtract the y values and then subtract the x values. So change in y over change in x times x minus 0. And here we see that the equation for the red line is y equals 6x. Okay. And then similarly, you can do the same thing for the blue line segment. Let's call that the function g. This is the line through the origin and 1, 5. And you see, if you'll do the same thing, you'll get y equals 5x, right? So I hope you can repeat that process for f, but I guarantee you'll get y equals 5x for the equation for g, okay? And then now for the area. I'm going to use vertical strips, so the integral would be with respect to x. And then since I have a dx, I need to find the bounds for x. What is the x value where the region starts, and what's the x value when it ends? It starts here, and that's x equals 0, right? And the region stops here when x is equal to 1. So the bounds would be from 0 until 1 of the height of the vertical strip. It's top minus bottom. So it's the function, the red function on top, so that's 6x, minus the blue function, which is the function at the bottom, it's 5x. And so this is just the area, is just the integral of x dx from 0 to 1. And this is just x squared over 2, evaluated from 0 to 1, and that is 1/2. So the area of the shaded region is 1/2 square units. Okay. Any questions? Is that clear?
By any chance, could we integrate both functions and then solve for them and then do that? Like, instead of subtracting the functions, could we subtract the results?
Yeah, that's also fine. You can integrate 6x from 0 to 1, then integrate 5x from 0 to 1, and then subtract the 2 results. That's fine. You'll get 1/2 as well, but that will take longer than this one. So I'd suggest you simplify the integrand first so that you'll just integrate one thing instead of integrating 2 things. But I guess that springs from your earlier interpretation that you are first getting the area under the red curve, and then looking for the area under the blue curve, and then you subtract them to get the area in between. And that's fine. Though computationally, it would be easier if you subtract the 2 functions first and then integrate. But that's perfectly fine if that's where you are more comfortable with. Okay. Now, problem number 2 is a bit more challenging in the sense that the second function, or at least for me, the second function cannot be graphed as easily as the basic functions that we know, because the first function is y equals x. That's fine. It's just a straight line passing through the origin, right? But 5x minus x cubed is a cubic function, right? And the thing here is that it's not a simple cubic function that we know how the graph will look like, because you have an extra 5x term in there. So, but remember, we need to have a good idea of how the graph or the regions look like, so we know what function is on top and what function is at the bottom, right? So the first challenge here, I guess, is to sketch the graph of y equals f of x equals 5x minus x cubed. And just to be sure, I will be careful here, so I'll have a good idea of how the graph looks like. I'm going to use techniques from Cal 1 in order to sketch the graph of the region. So here I'm going to use curve sketching techniques. And I hope you guys will take time to take another look at this from your Cal 1 notes. Maybe I'll start. Maybe I will borrow 2 more minutes to lay down the solution here, and then I'll ask you guys to continue it on your own, and then we'll start with the actual integral next time, right? So if you remember from Cal 1, the first thing is to compute for f prime and the critical numbers, which will tell us when is the function increasing and decreasing. And it also revealed the local minimum and local maximum for the graph or for the function. So if you look at f prime, this is 5 minus 3x squared. And then you equate it to 0. That will give you critical numbers x equals plus or minus root of 5/3. Okay, so I'm skipping some of the algebraic steps, but I hope you can do them in details once you try it on your own. Okay, so these are the critical numbers. And what's the purpose of critical numbers, if you remember? We'll make a sign chart for f prime and observe when it is positive or negative. And then the critical numbers serve as subdivision points. So that means I can divide the real number line to 3 subintervals bounded by the critical numbers. So we have 2 critical numbers here. Okay. And then you pick some test numbers on these subintervals. So for instance, here I'm going to choose -2. Here I'm going to pick the easy choice 0. And here I'll choose +2. And then I'll plug this into f prime. Those test numbers, -2, 0, and 2, I'll plug them into f prime and observe the sign. If you do so, you'll find that here it will have a negative sign. On the middle interval, you get a positive sign. And on the right interval, you get negative. And if you guys remember, what would be the interpretation of these signs? Well, from -infinity to negative root of 5/3, the function is decreasing. From root 5/3 to root of 5/3, the graph is increasing. And from 5/3 to positive infinity, the graph is decreasing. Yes, Robert.
Just like a little review on this. Which one are we plugging the critical numbers into? The original equation or the first derivative equation?
The first derivative.
Okay.
So here I'm doing a sign chart for f prime. That's why I wrote it here. Just a quick reminder. I'm plugging in the test numbers onto the first derivative. So I know the sign of the first derivative, because the sign of the first derivative reveals whether your function is increasing or decreasing, right? And then not only that, it also reveals whether you have a local max or a local minimum at the critical numbers. So because here, we know that the function is decreasing, right? So the function will behave something like this. It goes down. But after negative root 5/3, it will be increasing because you have a positive sign over here. So that means at this point, we have a local minimum, right? And then the function keeps on increasing until it hits the other critical number, right? And after that critical number, it will be decreasing. It will go down. So that means here we have a local maximum. And that will be helpful to see how the curve exactly looks like, right? So, and then the next step is to compute f double prime, because f double prime will tell us when is the function concave up or concave down. But since we don't have time for that, I'm going to leave it here. And I will ask you guys to try to review Cal 1 and try the second step and probably have a sketch of the graph. So I will include the rest of the solution here until the sketch of the graph in the annotated worksheet that I will upload today. So we can start the discussion by setting up the integral right away. But if you have questions on that, let me know on Friday. Kevin, the survey is located at the lab meeting channel. So it's one of the posts there. So you can see it there. Yes, Robert, you have a question?
When you find the second derivative equation and you set it, do you set it to 0 to find the critical points?
Yeah.
Okay.
Or more precisely, the hypercritical points. That will tell you what would be what are the possible points of inflection.
Okay.
And then you do the same sign chart. So yeah, try to review that, but I'll include the solution until the sketch of the graph in the annotated worksheet that I will upload later today. And then I'll just start the discussion by setting up the integral for the area on Friday. But don't worry, if you have some questions or difficulties with that Cal 1 concepts, you can let me know at the start of lab on Friday. Okay? Another question, Robert? Okay,
Oh,
probably you
sorry,
just
I just
forgot
didn't
to.
take it down. Yeah, my bad.
Okay, yeah, sure. So let's call it a day here, guys. Thank you for coming today. Enjoy the rest of your day and see you again on Friday. Bye, everybody.
Thank you. Peace.
You're welcome.